Good morning, everybody. Today I am starting the topic marine boilers. So, first I'll discuss in general marine boiler aspects, then I'll go towards turbine and we'll solve some problem. We'll discuss different issues, a different component, and some calculations also will include in this week lecture, week 4. So, first, when you discuss about marine boilers, first you have to see Rankine cycle. Rankine cycle is like this. You have one boiler. Okay, I'm just drawing like block diagram. Boiler, then boiler will be producing steam will go to turbine. Okay, so from turbine steam will be coming out, low temperature, low pressure turbine will be coming out, and it will go to condenser, then from condenser it will go to pump to boiler. Okay, this is the sequence. It will be happening in any steam turbine system. The steam turbine, it is being used for your locomotive application. For example, you can see this heritage train, a ship. Previously people were used to say like steamer. A steamer means it will be producing lots of steam, and steam will be driving a marine engine. So that's why they called it steamer. Now those steamer engine, like steam produced engine, is being replaced by diesel and other operated engines. And if you see train in India, uh, previously all trains were run by steam engine. Now gradually those replaced, and now only heritage trains are there which are run by your steam turbine system. Okay, now the thermal power plant, if you go to NTPC website, National Thermal Power Corporation, they are running all their systems, especially coal fired systems, using your Rankine cycle. Okay, so I have drawn one simplest Rankine cycle diagram. It will be having one turbine. Okay, so turbine will be producing work output, and boiler will be giving lots of heat. Okay, so heat given to water to produce steam. Okay, so in boiler you are boiling water, and water is taking lots of heat. Okay, when it is getting lots of heat, it will be creating steam, superheated steam or saturated steam or maybe unsaturated steam. So that high pressure, high temperature steam will go. So after boiler, the temperature T will be very high, pressure also will be very high. Okay, uh, after turbine, your temperature will be lower, pressure also will be lower. So after turbine to pump, the pressure will be same actually, because turbine and condenser is actually one pipe. I have already discussed during heat transfer calculation, that heat transfer lectures, that condenser actually it is lots of pipes will be there, and in pipe heat will be through the pipe heat will be transferred. So because the steam temperature high, ambient temperature is lower, so heat will be going out to the ambient. Okay, so heat will be, so I can write Q cold or low temperature, and boiler is giving Q high temperature, and pump WP, pump is taking energy and it is giving to fluid. So from where it gets energy, it will be getting energy from the turbine directly, or it will get energy from any electrical source, or any other fuel will be burnt and pump can be run. So this is the function of Rankine cycle. So Rankine cycle will be producing steam. This will be going to turbine system. So turbine system will be releasing that steam, low pressure, low temperature, that will be going to condenser. Condenser, there will be phase change. Phase change will be occurring. So steam will be liquid. Will be liquid again. Okay, in condenser, and that liquid or water, because this is water cycle or H2O cycle. So water will be pumped, liquid water will be pumped to boiler, and boiler again it will be producing steam. When it is producing steam, it will be high volume, high temperature, high pressure. When pump is working, pump will be working at very low volume because already is liquid. Liquid is having lower volume and it is working at lower temperature also, even lower pressure also. And boiler phase change occurring. So, phase change occurring in boiler, okay, and producing steam and producing steam, and pump is only delivering fluid or adding delivering fluid and adding energy to the fluid. So, already we discussed the pump will be adding energy. So, here we are using one pump. So, that pump can be like it can be centrifugal type pump or it can be jet type pump. Jet pump I will discuss later. A boiler, it is also having heat exchanger. Inside boiler there will be heat exchanger, lots of pipes will be there. So, whenever heat will be coming, heat will be going through the pipe and water inside pipe will be boiled, and finally the boiled steam will get more heat and it will be going to superheated condition. That superheated steam will go to turbine, turbine to condenser, condenser from this cycle will be going on continuously. So, I will draw the cycle again. Boiler, then boiler to I said turbine, this is my turbine, then turbine to condenser, condenser it is coming, condenser to pump, pump to boiler. So, this cycle will go on. Okay. Now, what is happening? I will put some number. From number I will start from boiler inlet, pump inlet here. 1, 2, 3, 4. Okay. Now, this whole cycle can be represented in TS diagram, temperature entropy diagram. So, previously I told that TS diagram will have one vapor envelope. So, this is called vapor envelope, vapor envelope, okay, and inside normally two phase will be there. So, liquid plus steam, liquid water maybe, okay, liquid water plus steam will be there, and this side this is called superheated zone, this is called superheated zone, superheated zone, and this is liquid zone. Okay, so left side of this envelope is liquid, pure liquid will be there, right side will be superheated zone, in between there will be liquid and steam, and this curve is called saturation curve. Vapor envelope is called saturation curve, saturation. Okay, so if you take certain fluid, if it is that fluid property lying on the curve, so it will, you can say this is a saturated fluid. Okay, if the fluid inside this vapor envelope, it is called unsaturated. So, this area will be unsaturated. Okay, and if the fluid property lying on the curve, so it will be saturated. Now, I want to represent this whole steam cycle on TS diagram. S means entropy, this T means temperature. Okay, I will draw the TS diagram again, TS, and vapor envelope again I will draw, and my loop starts from point 1. Point 1 will be left side, liquid I said. So, liquid vertically going up, then it is going to 2. You take certain amount of liquid, you are increasing energy, so temperature will be rising. So, temperature rising, then after that 1, 2 and 2 to 3, boiler will be heating water, then water will be changing phase, it will be steam, steam to it will be superheated steam, then 3 boiler exit, then again it will be going down because of turbine work, 3 to 4, 4 to 1, will be my condenser. So I have to put arrow direction. So whenever you are drawing a Rankine cycle, so you have to draw the whole diagram, and proper nomenclature and direction also should be given. For example, 1, if you put in wrong direction or wrong place, so your whole cycle will be wrong. Okay, so here 1 to 2 in TS diagram, it shows pump. Okay, 2 to 3, it is boiler. So pump adding energy to fluid. Okay, as per definition I already told. Boiler adding again energy to fluid and making steam. Okay, and 3 to 4, it is turbine. What is it doing? It is extracting energy. It is extracting. Okay, so if you have any steam turbine, you can see any locomotive or any steam turbine, national thermal. Okay, 3 to 4 turbine, it is extracting energy, and 4 to 1 condenser. So what it is doing? It is releasing heat, from steam and making liquid water. Okay, now you can see 1 to 2, this, if you see vapor envelope line, I am just making thicker line, this vapor envelope left side. So this is liquid side, right? So the point 1 is on this liquid line. So that means pump will start when fluid steam become liquid. Okay, and condenser will give liquid to the pump. Pump will not handle any gas. Okay, now pump will be adding some energy, it will reach to 2. So we are assuming this is isentropic process. Okay, this is ideal Rankine cycle. Okay, I am drawing ideal Rankine cycle. Practical, there will be some deviation, later we will discuss. So ideal Rankine cycle will have 1 to 2 isentropic process. So 1 to 2 pump adding energy. In ideal cycle, 1 to 2 ideal cycle, it will be isentropic. Okay, isentropic means entropy not changing. But in if you ask me what is the practical thing, so practical thing will be like this, envelope, and ideal this one. Practically we have to give more energy actually, so my curve will be like this. Okay, instead of 2 I will get 2 dash, I will have to add more energy. Pump will take more energy. Now 2 to 3, what is happening? 2 to 3, I can put like 2A, B. So 2 to 3, if you see, first I will say 2 to 2A, 2 to A. So 2 to actually sensible heating. Sensible heat addition. You got water at 2, pump gave some water, maybe say 40 ° centigrade temperature, but it must reach to 100 ° centigrade, then it will start boiling at 1 atmospheric pressure, right? So to reach 100 ° centigrade at 1 atmosphere pressure, you have to give certain amount of energy. So that is called sensible heating. So using one thermometer, you can measure that one. So 2 to A is sensible heating process, and A to B, phase change occurring. Okay, A to B, because inside vapor envelope, so lots this zone phase change will be occurring. So liquid to steam, it will be forming. Okay, when you are reaching to B, you are getting liquid to steam. Okay, now B to 3, what you are getting? B to 3 actually, at B is actually on saturated. This is saturated steam, at B. okay, and A saturated liquid, saturated, okay. Point A is saturated liquid point, point B is saturated steam point, right, B. So B to 3, what is happening? This is called superheated zone, superheated steam, okay. When you are reaching to 3 from B to 3, you are creating superheated steam. So at B you are getting saturated steam, let us say water 1 atmosphere pressure, 100 degree centigrade temperature, you form steam. Now you increase temperature further, do not change the pressure, okay. In that case what will happen, your temperature increasing and your entropy also increasing, so you are reaching to 0.3, okay, that is called superheated steam. Now if you want to reduce temperature, you want to make liquid, so temperature will go down to, it will come to B, then again it will start forming liquid droplets, okay. uh, and 3 to 4 actually turbine work. So inside turbine you cannot give liquid, so liquid will have some difficulty, so turbine will be handling only steam, so that's why you have to give superheated steam to turbine, and after turbine exiting it can reach to 0.4. So 0.4 saturated saturated liquid or saturated steam, you can say, okay. So 4 to 1 phase change will be occurring. So this is condenser work, 4 to 1 I have written condenser, so this is condenser, okay. So only condenser is giving only phase change, okay. This is because this is ideal cycle I am saying, that is why all the points are lying. For example, 0.4 is lying on the saturation curve, but in practically 0.4 may be inside or outside. B also, not B is not having any value. A, this 1.1 pump entry also can be maybe outside the curve, saturation curve. 0.2 also can be differing because of non-isentropic condition if it is practical, okay. So this is practical cycle will be like this, then it will be going like this, it will go, then it will be giving less amount of energy, okay. It will give energy, less amount of energy, so 1 2 2 3 4 1, so this way it will work, okay. So whenever you are drawing figure, you should draw the arrow direction also, you should write details of everything. I will draw TS diagram again. TS, some more things are there to explain here. I said like it is ideal cycle, so everything will be on ideal situation, okay. 1 2 3 4. So boiler, inside boiler 0.2 to 3 happening, so 2 to 3 actually constant pressure process, okay. So 2 to 3 it is inside boiler and pressure is not changing, it will be occurring in with isobaric condition, okay, constant pressure or isobaric condition, pressure process, and 3 to 4 pressure is getting changed. So 3 to 4 in for ideal cycle my entropy not changing, so it is, you can see, completely vertical, so isentropic ideals for ideal cycle. Even to 4 to 1 it is again constant pressure process, 4 to 1 constant pressure, again isothermal also, same temperature will be maintained, right, because phase change occurring during phase change temperature will not change, so this is isothermal process or temperature not changing. And 1 to 2 again isentropic, I am saying ideal conditions, okay. So ideal, practically things will be different, 1 to 2 and 3 to 4 especially turbine and pump work, it will be different, okay. So this is ideal cycle, and practical TS, practical will be like this, envelope I have ideal cycle first you draw, okay, then ideal cycle will be like this. Okay, 1, 2 dash, 3, 4 dash, 2, 4. So, you are giving more energy, you are getting less amount of energy. So, 2 dash 1 to 2 dash isentropic, non-isentropic. So, it is irreversible process. Irreversible process, whenever we say, actually we put some dotted line, that means it is not reversible. Okay. So, energy will be lost, entropy will be generated. So, entropy gone up, you can see this 1 to 2 dash line length is longer. So, that means you are giving more energy to pump. 3 to 4 you can see you are getting less energy from the turbine. Okay. So, these are both are irreversible process, 3 to 4 dash. Okay. This is a practical thing, but ideally we are for simplicity we assume that there is no entropy generation. Just for initial calculation we will go through ideal cycle. After that later stage we will go for go through this practical cycle, what are the different losses we will try to calculate.